You know, when you're spreading jam on toast, have you noticed that it's easier if you move the knife faster?
Yeah.
Well, it turns out that's shear rate in action.
Uh-huh.
It's a really simple concept, but it has a lot of implications.
Okay.
And today, we're going to dive deep into the world of fluid mechanics.
All right.
To see how far this idea goes.
So are you saying that, like, the speed that I'm spreading the jam
Yeah.
is going to affect how the jam behaves?
Exactly.
Wow. I never thought about it that way.
It's really interesting, isn't it?
Yeah.
And it turns out that it has implications for all kinds of things.
I can imagine. So like in industrial processes or even just like blood flow, you said.
Exactly.
Okay.
It affects how fluids behave in all sorts of different contexts.
That's amazing.
So let's get specific.
Okay.
How do we actually define shear rate in a way that helps us understand these complex systems?
Well, you can think of it like those layers of jam again. The top layer that's touching your knife, that's moving the fastest.
Right.
Right.
While the bottom layer is kind of stuck to the toast.
Yeah.
And shear rate is really just measuring how much that speed changes over the thickness of the jam.
So it's all about like the difference in velocity.
It is. It's all about velocity gradients within the fluid.
Okay. So the faster the speed changes over a given distance, the higher the shear rate.
Yeah.
That makes sense. But velocity gradients aren't the only force at play here, right?
Right.
What about the friction between those layers?
Yeah, that's a great point. That friction is actually what we call shear stress.
Okay.
And that's the force that you actually need to make those layers move past each other.
Okay.
So in really simple fluids like water or air, which we call Newtonian fluids, the relationship between the shear rate and the shear stress is actually pretty straightforward.
So if you double the shear rate, you double the shear stress.
Exactly. It's a very simple linear relationship.
Okay, so Newtonian fluids are like the easy ones to predict. Yes, they are very predictable.
But what about the fluids that don't follow the rules so nicely?
Right.
Is that where things start to get really interesting?
That's exactly where things start to get really interesting.
Okay.
We call those non-Newtonian fluids.
Okay.
And they are anything but predictable.
So unlike water, where the viscosity is pretty much constant, these non-Newtonian fluids can become thicker or thinner depending on how quickly they're being sheared.
Exactly.
That's wild.
It is, and it leads to some really interesting behavior.
So, like, what kind of fluids are we talking about here?
Well, think about ketchup.
Okay.
Ketchup is a great example.
Okay.
It's thick and stubborn when it's in the bottle. But if you give it a good shake, suddenly it flows really freely.
Right.
And that's because ketchup is what we call a shear thinning fluid.
So the faster it's sheared, the less viscous it becomes.
Exactly. The viscosity decreases as the shear rate increases.
Okay.
That's why it flows easier when you shake it.
That's a perfect example. And I'm guessing there are fluids that do the opposite, right?
You got it.
They get thicker under stress.
Yeah, those are called shear thickening fluids.
Okay.
And a really good example of that is a mixture of cornstarch and water.
Oh, yeah.
You can actually run across a pool of it.
Yeah, I've seen those videos.
Because when you apply that pressure, when you apply that stress, it temporarily solidifies.
Wow.
But if you stand still, you'll sink right in.
So it's all about how much stress is being applied.
It's all about the shear rate.
Okay, now I'm really starting to see how this all connects to the real world.
Yeah.
It seems like controlling the shear rate in these fluids must be important for all sorts of things, from manufacturing to medicine.
Absolutely.
But before we get ahead of ourselves, I'm curious about how we even measure something as dynamic as shear rate.
Yeah, that's a good question.
How do you do that?
Well, the way we do it depends on the type of flow that we're actually analyzing. One way to do it is to measure the velocity of the fluid at different points.
Okay.
And then calculate the rate of change. So, for example, imagine you have fluid flowing through a pipe.
Okay.
The fastest flow is going to be in the center of that pipe. Right down the middle.
Right.
But the fluid that's actually touching the walls of the pipe is going to be pretty much stationary.
Right.
And so that difference in velocity, that's what gives us the shear rate.
So the highest shear rate is at the walls of the pipe.
Exactly.
That the velocity gradient is the steepest.
Exactly.
It's like a sliding door.
Yeah.
Where the track experiences the most friction.
That's a great analogy.
Okay.
Another way to measure shear rate is in a more controlled environment.
Okay.
Like between two plates. So if one of those plates is stationary and the other one is moving, then the shear rate is just the velocity of that moving plate divided by the distance between them.
Okay, so there are a couple of different ways to actually measure this.
There are.
It seems like understanding shear rate is about more than just describing how fluids flow.
Right.
It's about being able to predict and control their behavior.
Exactly.
Which must have tons of practical applications.
Absolutely. And those applications are actually what we'll be diving into next.
Okay, great. I'm looking forward to it.
So we've talked about how shear rate is a measure of how those layers of fluid move past each other. And when we bring forces into the picture, that's where shear stress comes in.
Right. And we were talking about how shear stress and shear rate have this really straightforward relationship.
Right.
At least in Newtonian fluids.
Exactly.
But when we start talking about these non-Newtonian fluids, things get a little more complicated, don't they?
They do. For Newtonian fluids, the shear stress is directly proportional to the shear rate.
Mm-hmm.
So if you double the shear rate,
yep.
you double the shear stress.
Yep.
It's a nice, easy relationship.
Okay.
And it's captured by what we call Newton's law of viscosity, where that constant of proportionality is what we call viscosity.
So if viscosity is the resistance to flow, a higher viscosity means you need more force to actually create that flow.
Exactly.
That's why honey flows so much slower than water.
Exactly. Honey has a much higher viscosity than water.
It all makes sense.
It does. And that linear relationship makes it pretty easy to calculate.
Yeah.
Shear stress in Newtonian fluids.
Huh.
But then we get to non-Newtonian fluids.
Right.
And that nice, neat equation goes out the window.
Because their viscosity isn't constant.
Exactly. It changes depending on the shear rate.
So how do we even begin to model and predict the behavior of these fluids?
Right.
It can't be as simple as doubling the shear rate and expecting the shear stress to double right.
It's not. We need more complex models. For example, something called the power law model.
Okay.
It can be used to describe how the shear stress and shear rate relate to each other.
For non-Newtonian fluids?
Yes, in non-Newtonian fluids. And this model introduces something called a flow behavior index. And this helps us quantify whether a fluid is shear thinning or shear thickening.
Okay, so this index is like a measure of how much a fluid's viscosity changes.
Yeah.
With shear rate.
Exactly.
So a higher index means it changes a lot.
Right.
And a lower index means it changes less.
Yes, exactly. And a flow behavior index of less than 1, that indicates a shear thinning fluid.
Okay.
So as the shear rate increases, the viscosity decreases.
Okay.
So it flows more easily. Paint is a good example of that.
So we want paint to flow easily when we brush it on.
Right.
Meaning low viscosity at high shear rates.
Exactly.
But then once it's on the wall, we want it to stay put.
Right.
Meaning higher viscosity at low shear rates.
Right.
That's a pretty clever application of shear thinning behavior.
It is. Now, on the other end of the spectrum, a flow behavior index that's greater than 1 means we have a shear thickening fluid. Like that cornstarch and water mixture we were talking about before.
So in those fluids, the harder you push,
yes,
the more viscous they become.
Exactly.
That's almost counterintuitive.
It is, but it has some really interesting applications.
Like what?
Well, one potential application is in liquid body armor. So imagine a material that flows like a liquid under normal conditions.
Yeah.
But when it's impacted, the increased shear rate causes it to thicken and harden almost instantly, providing protection.
That's incredible. It sounds like something out of a sci-fi movie.
It does, doesn't it?
But it's based on real science.
Yeah. And it really shows that this isn't just some theoretical concept.
Right.
It can actually lead to really interesting innovations.
Absolutely. And the applications go far beyond just body armor.
Oh, yeah, definitely.
I mean, in food processing, you can control the shear rate during mixing.
Right.
To make sure things like yogurt and sauces have the right texture.
Exactly.
Or in biomedical engineering. Understanding how blood flow changes under different shear rates is crucial for designing artificial hearts and other devices.
It is.
It's amazing to think that something as simple as how fast fluids move past each other can have such far-reaching implications.
It is. But like any scientific field, there's still a lot we don't know, especially with these complex non-Newtonian fluids.
So what are some of the areas where our understanding of shear rate is still limited?
Right.
What mysteries are scientists still trying to unravel? We've been talking about these amazing applications of shear rate.
Yeah.
But it sounds like there's still a lot we don't know.
Right.
especially when it comes to those complex non-Newtonian fluids.
Yeah.
So what are some of the big challenges that scientists are facing in this field?
Well, one of the biggest challenges is accurately modeling the behavior of these fluids.
Okay.
Especially when you have multiple components. Real-world fluids are rarely simple. They usually have all kinds of ingredients mixed together.
Yeah.
And those interactions can make things really unpredictable.
So it's like trying to predict the outcome of a game with 100 players, each with their own set of rules.
Right.
And constantly changing strategies.
Exactly. And to make things even more complicated, you have things like temperature and pressure that can really influence how these fluids behave.
Oh, yeah, of course.
And a lot of fluids that we see in industrial settings actually contain solid particles, too.
Okay.
So that adds another layer of complexity.
So even with those sophisticated models, like the power law, trying to predict how these fluids will behave in real-world situations is still a challenge.
It is a big challenge.
Are there any specific areas
where
our understanding is particularly lacking?
Yeah, one area that's really tricky is turbulent flow.
Okay.
In non-Newtonian fluids.
So turbulence is already a really complex phenomenon. Even in Newtonian fluids. You have all those unpredictable swirls and eddies.
Exactly.
But when you add in the non-linear viscosity of a non-Newtonian fluid, it gets really hard to predict what's going to happen.
It gets really messy.
So it's like trying to solve a puzzle where the pieces are constantly changing shape.
Exactly. And that lack of understanding can have real consequences.
How so?
Well, for example, if you're trying to design efficient pipelines for transporting oil, which is a non-Newtonian fluid, you need to be able to predict how it's going to behave. Under turbulent conditions. If you get it wrong, you can end up with inefficiencies, wasted energy, and even safety risks.
It seems like the more we learn about shear rate, the more we realize how much more there is to discover.
Absolutely.
But even with those challenges, the advancements that we've made have led to some incredible breakthroughs. So what are some of the areas where this knowledge is making a real difference?
Well, one really exciting area is microfluidics, which deals with these really tiny volumes of fluids. And understanding shear rate at these really small scales is crucial for developing things like lab-on-a-chip devices.
So we're talking about shrinking down entire laboratories to the size of a microchip.
Exactly.
That's incredible.
It is really amazing technology.
How does shear rate play a role in that?
Well, you need to be able to control the fluid flow within those tiny channels. So you can do things like mixing, separating, and analyzing samples.
Wow, that's amazing.
It is.
What other fields are benefiting from this understanding of shear rate?
Well, another promising area is material science. By understanding how shear rate affects the molecules within a material, scientists can engineer materials with unique properties, like materials that can change their viscosity on demand.
So you're talking about a material that could go from flowing like a liquid to being as rigid as steel, based on the forces applied to it.
Exactly.
Wow, the possibilities are endless.
They are. I mean, imagine self-healing materials that can respond to damage by changing their viscosity.
Wow.
Or smart fluids that can adjust their flow in real time to optimize performance.
That's incredible.
It is.
It's amazing to think that this simple concept of shear rate is driving all these groundbreaking innovations.
It really is.
It's been a fascinating journey.
Yeah.
Exploring the world of shear rate.
It has.
From those everyday examples like spreading jam on toast to cutting-edge scientific advancements.
Yeah.
It's clear that shear rate is far more profound and impactful than meets the eye.
Absolutely.
I really appreciate you coming on the show today to talk about this.
It was my pleasure. Thanks for having me.